Okay, now let's calculate the acceleration. And again, we're going to do the first mass trial where we had just the 50 grams hanging on it. We've just calculated what V1 and V2 are. So now we're going to figure out what the experimental acceleration is and compare it with a theoretical acceleration. So if you see the first equation up here, this should be readily recognizable. This is from the kinematic formula. This is one of our kinematic formulas is usually number 3 on the list. V2 squared minus V1 squared is equal to 2a times x1 minus x0 or x2 minus x1, however you want to say it. This actually is related to energy conservation, kinetic energy and stuff, which you'll find out a little bit later. So what I want to do is solve for a. I want a. So a, to find the acceleration experimentally, we take V2, square it, subtract off V1 squared, and divide by 2 times delta d. In this case, delta d is going to be the difference, the distance between the two velocities. Now, if you remembered what I said, was that with the track, I had photo gate 1 and 2, actually it was going in this direction. So photo gate 1 was 50 centimeters, and photo gate 2 was at 90. So in this case, delta d is going to be 0.400. So delta d is 0.400 for all the mass sets. So let's go ahead and calculate the experimental acceleration for our first mass trial. So we know V1 was average, from the average time is 0.2152 meters per second, and V2 is equal to 0.5762 meters per second. We also know that the delta D is 0.400 meters. So I know there was another delta D in there. That was from measuring the velocity. Now we're looking at we're looking at the whole track, and the cart's moving through 2 different photo gates. There's a velocity V1 at this photo gate and a velocity V2 at the second photo gate. The distance between them is what goes down in this bottom formula. Now this next formula is the theoretical one. So once we do the experimental one, then all we have to do is plug in the mass on the string, which is 0.0489, over the total mass, which was, what did we say it was? 1.179.8 or something like that. So times 9.8. So we're going to do that after we do the experimental one first. So what do we need to do? We need to find V2 squared minus V1 squared. So why don't we just plug everything in? So we've got V1 squared. So I'm going to put 0.2152 squared minus V. Oh, I did that. I got to do V2 minus. Oops. V2's got to come first. V2 is 0.5762 meters per second, and then you square it, minus V1 squared. And it's over 2 times delta D. So you put 2 times delta D is 0.400 meters. Okay, so that's our acceleration, experimental acceleration. So you can now take your calculator out and figure it out. So again, I have a simple one, so I'm going to do it step by step, 0.5762. I'm going to square that. So I get 0.332 meters squared per second squared. And then I'm subtracting off 0.2152 squared. So that's 0.0463 meters squared per second squared. And then that's over 2 times 0.4, well, hopefully you know that's 0.8 meters. So notice one of the meters, I'm sorry there, you weren't watching me write it down. So this is V2 squared, this is V1 squared, and divided by 2 times D, which is 0.8. So now all we have to do is take 0.332, subtract out 0.0463, divide by this, and we get our acceleration. Notice the meters in the bottom will cancel out one of the meters on the top, and we're left with the correct unit for the acceleration. So I am going to do that right now. I'm going to take 0.332 minus 0.0463 and divide it by 0.8. And I get 0.357 meters per second squared. So that's my experimental acceleration. Now, let's look at the theoretical acceleration. So notice that's less than 1. The acceleration of gravity is 9.8 meters per second squared. So for this small amount of mass, 50 grams tugging on it, it's really not that much. It's because the mass of the cart and everything on it is still quite a lot bit larger. So acceleration is fairly low. It's less than a tenth of gravity. But you'll find out when you put more mass on the end of the string and it's tugging the cart more, this acceleration is going to go up. So let's do a theoretical acceleration. A theoretical, that's the mass on the end of the string, 0.0489 kilograms, divided by the total mass of the system. That's 1179.8 times 9.8. All right, so let's just do that out on my calculator here, and you do it the same way. I divide up. I want everything in kilograms, so to see what I made a mistake, I put 1,179 initially. It's 1.1798 kilograms. And the kilograms cancel out. 9.8 has meters per second squared. So just make sure you convert everything to kilograms, or else you almost made the same mistake I just did. 1798, okay, times 9.8, and I get 0.406 meters per second squared. And again, here's your theoretical acceleration. Notice how it's a little bit higher than the experimental. That's normally how it works with these things. Even though I accounted for friction, and you saw that I tried to account for friction, you did hear sound, right? I could hear squeals and stuff like that of the wheels sometimes. And even if it wasn't like squeaking, I could hear it rolling. So that's sound energy. Some of the energy is going into sound energy, is taken away from the system. When we derived this theoretical value, we assumed that the only forces acting in the system were that of that hanging mass. In reality, there's other forces acting in the system. There's a friction, there's sound. I mean, the cart is going through the air, so there's friction due to it hitting the air and stuff like that. So there's other forces acting on it, but those forces are really difficult to calculate in a closed form solution. But you can see it's, they're close, but what we want now is to find the percent difference between these two. So both of them have measured values in them. We measured the mass here, so we have to do the percent difference. And remember what that is? It's value number 1 minus value number 2 divided by the average. So we take 0.406 minus 0.3571 and divide it by the average. I'm sorry, I can't see it here. So the average is 0.406 plus 0.3571 divided by 2. So you take the difference, divide by the average, multiply that by 100%, and that's the percent difference. So let's just do that really quick, and then we will see. So I got 0.0489 for the top, and the average was 0.406 plus 0.3571 divided by 2. So 0.38155, then you can get it multiplied by 100%. So again, you guys probably can do it all in one on your calculator, but just make sure you put parentheses in, so and then multiply it by 100. So it looks like I got around 12.8% for the percent error, which isn't that bad for this type of experiment. We don't have a perfectly frictionless free track, and there's air, and you can hear the sound energy and things like that. I try to make the masses not move. That's another error that can occur. If the masses move around, it actually will absorb some of the forces. Okay, so now on to the next exercise.